Uf, me salvé.
¿Cómo?
Me salvé.
Ahora si todo lo que digas
Será tu contra. Será tu contra.
te darán adelante.
Okay.
So now we continue with our summer school. It's a pleasure to introduce Juan. Who will continue with the talk about condensed mathematics.
Okay. Thank you, everyone, for being here in the second talk this morning. So yesterday we saw a little bit of an introduction of the subject of condensed mathematics. We tell a little bit of the motivation behind, at least once, the theory why condensed sets are useful and what problem they solve, like trying to make a topology as algebraic as possible. And today, the goal is to explore a little bit more this category of condensed abelian groups, and maybe to argue that many constructions or computations you do in the classical world, they also hold in this setup, in at least, well, they also hold here, so at least it's not just a random generalization, it's a generalization that recovers already existing, let's say, computations, definitions, and so on. So for this, let me just, well, I think that it's important to mention this. So, well, what I explained yesterday was kind of the foundations of condensed mathematics at the beginning, where we use all profinite sets and so on. Nowadays, there exists a slightly different approximation to condensed math that somehow is included into the previous version, but that is more light. It's easier to access. So the name is literally light condensed math. And the idea is basically, well, let's say in practice, all compact half-order spaces, let's say, are too large. So when we do analysis, again, we don't care about some random non-countable product of, I mean, very big non-countable product of, I don't know, finite sets. This is something that maybe shows up when we do some, I don't know, point set topology, very abstract arguments. But in analysis, when we just care about Van Frechet spaces, p-adic, I don't know, locally complex vector spaces, these things are not necessary to study them. So the proposal of Scholz, Clausen, and Scholze is, well, maybe, well, with this theory, we have like very nice framework to do condensed mathematics, but we can just take something slightly smaller that at least is enough for everything that appears in practice in what analysis regards, and also maybe what usual algebraic topology or complex manifolds concerns. So instead, sorry for my grammar, instead consider something that, well, I'm going to call the Hausdorff light. Well, that's their name. I like the name. Which consists on metrizable compact Hausdorff spaces. Again, the idea is that basically any space that shows up in practice cannot be rebuilt from these ones. And you don't need to take like arbitrary large and more strange compact Hausdorff spaces. In practice, I mean, again, in analysis and maybe usual topology and yeah, these two. I mean, of course, like there are very interesting theorems appearing here, but maybe more related with logic or set theory or something like that. But this is more like from this side. For analysis, this one is usually enough. So similarly, well, so this, well, like these metrizable compact Hausdorff spaces, inside them you can look at the profinite ones again. So again, you can define something different. So prof light is, well, I mean, you can just say in this way, it's just the metrizable compact Hausdorff spaces, which are profinite. And there are equivalent ways to look at these spaces. So there are equivalent definitions. Maybe the simplest one for me is the following. So this category of like profinite sets are precisely those, the pro category, again, just formal limits which are countable of just finite sets. So basically it says that S is in here as long as you can write S as a countable limit of finite sets. So something that is not too crazy, it's just limits, countable limits of profinite sets. For example, p-adic numbers are inside this, and many others numbers are inside here. And again, you will have the proposition. Yes?
The limit means
projective limit, yes. Limit is always projective limit for me. Call limit means injective limit. Yes. Maybe if you want to stress the arrow to the left. So proposition, if you take something in here. So yesterday I mentioned that you can always cover using some profinite set. Well, if you put the board light, then the same works. So for example, we saw in the example of the interval 0, 1 of the real numbers that is just a quotient of countable products of numbers between 0 and 1 and 9, for example. So again, we can just redo all what we discussed yesterday, just using this framework instead. And maybe before jumping to condensed abelian groups, let me say what this situation is actually pretty useful. Is that at least algebraically, it's more pleasant to work with light condensed sets. And the reason is that, well, actually, another lemma is that if you have some kind of random like the profinite set, then there exists a surjection from the called Cantor set, which is just a product of 0 and 1 mapping to S. So this one is called the Cantor set because the usual argument of the Cantor diagonal is basically just looking at some elements and this product, just proving that this product is countable. So basically just saying that, well, I mean, this, you've used the random profinite sets, they could be like very complicated and it's not easy to know or to write down these things concretely as quotients of something. They are just limits of profinite sets. But if we are more in this work, which is light profinite sets, then everything is just a quotient of this guy. Of course, there are many quotients, but at least they are just up to isomorphism a set of quotients of this, which is not true for profinite sets because the kernel can grow that. So for technical important reasons coming from set theory, it's also better to work in this realm. So from now on, everything I'm going to mention, just going to focus in the light setup. So in particular, whenever I say a profinite set, I will implicitly say that it's a light profinite set unless I say something, unless I specify the opposite. And for me, condensed sets are going to be, by definition, sheaves on light profinite sets with the same topology that we just defined yesterday.
The light compact Hausdorff space is still capturing all the important objects, right?
Yes, it's still capturing the important objects because, for example, it still captures like spaces which are metrizable, for instance, or locally metrizable. Still, these are captured by these ones. Because essentially, whenever you have like a metrizable space and you have a compact Hausdorff space inside, this compact Hausdorff space is going to be metrizable as well, just coming from the metric of the big space. So anything that is metrizable, which is basically what appears in analysis, is kind of in here. And
So the Grothendieck topology with finite light.
it's exactly the same, yeah. It's just projections that, as we saw yesterday.
So the sheaf over the prof light are you can prove that are the same. So
They're different.
ah,
But this one embeds into the other one. Like these shifts are going to embed in the biggest category of condensed sets that we saw. It's just some kind of a small piece, a smaller piece of condensed sets, which are basically condensed sets that can be reconstructed from profinite sets.
I have the impression that last year condensed sets were sheaves over the prof light.
Yes. And this one maybe I would like to call it light if you want to be more precise. But because I don't want to put light but the official name of this should be light condensed sets. Just that I want to avoid putting light just to not write in light every time I word this.
Okay, but the difference between there is interesting, or is more interesting in this one?
I mean, someone is basically as different as, is it as different as this? Well, actually more tricky than that. The difference is interesting, but maybe not for analysis itself. It's more interesting for logic. Okay, there are some kind of logic that is more interesting when you work in the whole condensed category that you don't work in this little one, and things become interesting. But some kind of, let's say that this category, at least once for doing algebra and doing analysis, is less pathological than the other category. The other one still, you can do a lot of things, but it's not very clear. Some facts are not very clear to prove. For example, some flatness of something we're going to see later is not clear that actually doesn't hold in the other category, but it's going to hold in this category. So there are several reasons to just change to this one. Hopefully, we're going to see some of them in the course of these lectures. Yes. So let me take a remark, is that you can prove that condensed sets, and let me stress the light in here, is a full subcategory of just condensed sets. So again, just capturing like some objects in here, but which are more than enough to do what we want to do in arithmetic geometry. Okay, so after this small digression, let me go back to actually the subject of the talk of today, which is condensed abelian groups. So again, we can just make a definition. I think I just briefly mentioned yesterday, but let me be more explicit. Well, a condensed abelian group again is a sheaf on, and maybe let's stress profinite light. Again, you should call these light things, but let me just drop the light in the notation from now on abelian groups. I mean, like, as I said, you can define condense something for something being basically any algebraic structure or category. So usually we denote this cond ab. And again, if you want to write it in these worlds, it's just the sheaves on profinite sets on abelian, with values in abelian groups. Okay, so something like the first kind of properties you can always prove for abelian objects inside of a site, this is just the same as abelian object in a site, are the following. I don't know, we'll say the proposition. Well, because this site is small, like basically this is up to isomorphism classes. There are just a set of them, which is kind of important. Then this thing is what is called the Grothendieck abelian category. So it's an abelian category that has a generator, and I think that you need maybe something else, but like, for example, direct sums are exact, filter colimits are exact. Well, it's an abelian category, it's already something, and has a generator that you can build up using this Cantor set. So it's a very nice category. So it's a very nice, very good abelian category. This is maybe the way you should read this. That behaves pretty much like sets do. Moreover, it has a couple of axioms. I think this is some version of countable AB4, maybe asterisk or something, which means that countable products are exact. So this is something that well, like you are working in sets and you have like short exact sequences of sets or indexed by some other set or family. Then if you take the product of these short exact sequences, you get also a short exact sequences of sets. So if you were working with the whole category of content sets, the same will hold with content sets. Also, products are going to be exact. In this late setup, there are things you need to be very careful. Maybe products are not exact, I don't know, but at least countable of them, they're going to be exact. Which is, again, enough for many things. You don't, sometimes you don't care about taking all products when you do analysis. You just get taking about countable of them. Sometimes it's more tricky. And well, there is another property. A countable version of something that is called AB6, which is some kind of weird property that commutes colimits with products in a suitable sense. So I will let you to just look what these actions are and maybe go to the, by the way, so for references, I will ask Hector to put it in the webpage on the school. For I think it's easier to access. I will be a page, a link with maybe some PDF with has references and maybe a couple of things more. So I think that would be easier than just writing out references here. Okay. Yep.
From exact, you are meaning that.
Send short exact sequences to short exact sequences.
All right.
Okay. So in other words, let me again not get proof this in the references. So this thing just is saying that condense. Recall that one of the motivations was to obtain a category that is an abelian category, and not just an abelian category, but a nice abelian category that somehow generalizes topological groups, topological abelian groups. So as we saw yesterday, a huge class of topological spaces embed into condensed sets, and then it's going to be formal to prove that the class of abelian groups in these topological spaces is also going to embed into condensed abelian groups, something that you can just do maybe as an exercise here. So this category at least is making at least this goal concrete. You're defining the category that does the job. Of course, to argue that this is a good category, you still need to understand this category a little bit more. So let's do that. So the first thing you can do whenever, again, you take abelian shapes into a site is a very general construction, which is like the free object in this case, a condensed set. So you have a forgetter functor. From condensed abelian groups to condensed sets. Again, because any condensed abelian group just has an underlying condensed set. And this functor has a left adjoint. This is left adjoint, again, because it just ships on a site, is something that you can always construct sort of explicitly. It's something that, at least abstractly speaking, is going to say that condense set T into something that we denote set of T, just standard notation maybe for the free object, in this case a condense set. And this guy is the sheafification. In the Grothendieck topology that we just impose into Lie profinite sets of the pre-sheaf that maps a profinite set to the free abelian group generated by the S points of T, which is, again, something purely sets, nothing else. And it's just, again, an exercise maybe once you work in the site, that this construction is going to give you the left adjoint of this map. So, okay, this is a definition, but this works in any site. But can you say something more about this, guys? And the answer is yes. At least, let's say that any condensed set is essentially by construction, it's just sheaves on profinite sets by definition. And any sheaves on profinite sets, they can be written as a quotient of representable sheaves. Again, something always general from maybe additive representable sheaves, something general from Grothendieck sites. So in order kind of to understand how this thing looks like, it's more or less enough to understand how it looks like for profinite sets. And from there, you can start to spread out along more general spaces, for example, compact Hubble spaces. So this is actually the content of the following proposition, is that you actually have an explicit description of the free abelian group of a profinite set in terms of, well, just profinite sets itself. You can write it down explicit formula. So let S be a profinite set. Recall that I just dropped the norm light, but this one is supposed to be light with Sn finite. Maybe let me define set of Sn of, I don't know, let me use a 1, this is equal to K, to be the sums S in Sn of AS S, the set of sums, such that the sum of the AS is less or equal to K. So these are just tuples of elements in Sn whose L1 sums, with just absolute value of the sums is just major by K. So this is a finite set.
In prime?
Sorry?
In prime?
This is supposed to be a 1. Making reference to the fact that I'm taking this sum like this. At the end, well, it doesn't matter which one you take, it's going to be the same, but let me. So this is a finite set, which is a finite set. So then, the free, right, the free condensed abelian group generated by the group S is actually isomorphic to the union along K of the limit of the finite sets like this, where you can see this guy inside just the limit of all these finite sets. So indeed, well, this thing is a subspace of just the limit of taking this kind of limit of the free groups in finite sets. And it's a precise limit, a limit of something that we can compute at least keep a formula in terms of just a union of profinite sets. So know that this is just a union of profinite sets.
Sorry, AS relies on what space?
Sorry?
AS,
These are just integers.
just integers?
Yes.
All right.
Pure integer. So in some sense, maybe something to highlight that would be important later is that this space, you can think of this space as the dual of taking the continuous functions of S into Z, thinking like this. This is because these continuous functions, because this one is profinite and this one is discrete, it's also just the colimit of the continuous functions of the finite sets. And then you just take a limit out here. So this space is some sort of a space of set value measures of the profinite set, kind of by construction. It's just the dual of continuous functions. This is how measures are usually defined abstractly. And it's telling you that this one C space is somehow a weird specific class of measures, of set value measures of the set. At least this is the interpretation that was first given to kind of these free objects here. You should think about these ones as some kind of measures, maybe very rough measures, but some kind of measures in the profinite set S. So there would be a similar computation that you can express, I think, for compact Hauser spaces, maybe. Maybe not sure about that. But anyway, this gives me more very precise formula for this. Okay, well, the proof requires some work, but let me not address the work.
The K is also integer.
Sorry?
K is varying over integer in this.
The case of?
The K.
The K is, I mean, it can be any real number, but yeah, let me just put this. Right.
This DS here, this is an abelian group, not a condensed abelian.
That's a condensed abelian group. But this one is, well, any discrete, any usual group, you can see it as a condensed abelian group because it's just a union of points. And the point is another condensed abelian group. It's a final object in condensed abelian groups. Yes, so maybe something to remark is that when you have sets just embed into condensed sets in, well, just a natural way, just by taking a point to the point and then just sending unions of points just to unions of points. So we'll try to basically look at these objects always as condensed sets. All right. Okay, so we have a more or less a control on the free objects on profinite sets in the sense that we can write down explicitly what they are, so they don't look that scary anymore. And this category of condensed abelian groups, again, we wanted something that had some algebraic flavor, and in order to do algebra, well, we need a tensor product. So the category of condensed abelian groups has a tensor product. Again, this is not special for this. This holds whenever you take abelian objects in a site, so this is not something surprising. But you can compute in the following way. I mean, like, at least you can define it the following way. For any two condensed abelian groups, the tensor product of them is the simplification of the functor that sends S to, well, we can take M of S, N of S, and take the tensor product over set. I think it doesn't matter if you take over set over something else. So this is something that, again, always holds abstractly whenever you work with a site. The condensed abelian groups on the site is going to be just a tensor product, and tensor product is abstractly just defined in this way. This is nothing special. However, in condensed mathematics and maybe in analytic geometry, when we take tensor products of things like Frechet spaces or Banach spaces, we usually take some sort of completed tensor product. At least this is what we actually want to take. Or when we do like maybe p-adic geometry, of formal geometry, we take some kind of adically completed tensor products. This one is not one of them. So it still is a tensor product of objects that look like topological abelian groups, but this tensor product is not complete. It's not completed. So for example, you could take the real numbers and take the real numbers and tensor with itself, and well, you would like to have a tensor product such that the tensor of the reals with the reals is just the reals, because this is what there is maybe not other. I mean, completed tensor product should behave like this. But with this one, which is just a purely condensed, it does not. So if you take this one, it's just some condensed abelian groups, which will exist. Makes sense, but it's not something that comes from usual topology. For instance, if you take just the points of this thing, this is just the usual algebraic tensor product of the reals with the reals, which is just highly transcendental. It's just huge. So, okay, this is a problem that we need to solve. Hopefully we're going to talk about this in next talk. But today we'll keep with the fact that there is a tensor product that we have in there. So whenever we have this tensor product, we are in a category that has colimits, because condensed sets again just has all colimits, limits, and so on, because it's just abelian shifts in our site. Then one can always take the right adjoint of the tensor product and promote the mapping spaces between condensed abelian groups to an internal home space. So by taking right adjoints, one has an internal home. So concretely, for M and N condensed abelian groups, well, the internal home ought to be a condensed abelian group. So in order to define it, I need to give you the points on a profinite set. Again, a light profinite set. So I can give you the points on here. And well, if you want this one to be an adjoint to this, there is basically just one only thing that you can do. And the answer is basically, this is just the usual ohms, so which is just a set, or maybe an abelian group, from M tensor set of Sn. So again, you're kind of forced to do that if you actually want this to be the right adjoints of the tensor. So you can define S this way, and maybe something to remark is that, well, here we did it with condensed abelian groups, but it's something you can also do directly with condensed sets. So it's maps also we call this enrich in condensed sets, where this time for T and X maybe in condensed sets and S profinite, you can define this internal mapping space, which is going to be a condensed set. And this one, again, you construct it in such a way that is adjoint to just taking the product of condensed sets.
These are already cheap. Do you need to shiftify?
This one is not necessary to shiftify. This one you can just check that it's actually a shift, directly a shift, yes. Mostly because it's going to be a right adjoint, so it's going to behave well with limits, and right adjoints and limits commute, so to speak, in this kind of explanation. Well, this one is going to be more like a left adjoint, and this one presents co-limits, and with limits it behaves a little bit weird. Like, could be, you need to shiftify for this one too. But this one is okay. This one is literally the formula you get. Okay. It's okay. We have this tensor product. We have the internal home, and a natural question is, well, what happens if you start plugging in maybe a very condensed abelian group that come from classical topological abelian groups? What do you get? Like, you expect to get something that is reasonable. And the answer is yes, you get something that is reasonable and something that we already have defined from decades ago. So let me state the following proposition. And maybe just even just do the proposition in this case, for which I'm going to deduce something about condensed abelian groups. So take x and y topological spaces. Maybe let me just, for safeness, say Hausdorff topological spaces. Probably is not important. Well, maybe it is. I don't know. Let me just say Hausdorff to be safe. And let me assume that x is compactly generated as we saw yesterday. Like just its topology is completely determined by map from compact Hausdorff spaces or from profinite sets. Again, maybe you want to put the word light everywhere, but sorry, this is awful. So some classical construction that you can do in topology is in order to endow, so consider continuous maps from x to y. And a natural topology you can always input into these continuous maps is this so-called compact open topology. Right? Something that, for example, is used whenever you talk about Pontryagin duality in locally compact abelian groups. This is the topology that you put into the mapping spaces for the dual. So then there is a natural, meaning functorial isomorphism. Oops. Of condensed abelian groups, condensed sets, which is between, well, we have this condensed mapping space between the condensification of these two topological spaces, but also we can just take the condensification of this topological space. And well, turns out to be equivalent. And maybe I would like to put a map, I don't know which way. It's more natural to put a map. Maybe this way. And maybe let me just conclude what happened for this. So in particular, if A and B are topological abelian groups, like Hausdorff topological abelian groups with A compactly generated, then, well, you can also consider just the condensed internal home in our condensed abelian groups. And you can consider the continuous maps between A and B, also endowed with the compact open topology. And these two are equivalent. And this one is going to be a consequence of this after you just write down this basically as a closed subspace of this one satisfying some diagram. So sketch of the proof of this, and let me just construct a map.
Did you also need to put underline on
Sorry? Yes, thank you. They want to make this, thank you, explicit that, yeah. For this proposition, I want to see these ones this way. Thank you. So sketch of the proof. So it's something that a property that you have with the compact open topology. So you have a continuous map. X across a mapping from X to Y to Y. So the evaluation map is just taking, well, X a function evaluating is continuous, basically by construction of this compact open topology, and maybe for that you also need this one to be completely generated. And this evaluation map, it gives rise to a map from the condensification of this diagram, of this furrow, which I recall that the condensification has a left adjoint, so in particular it commutes with a limit, so in products. So the condensification of the product is just the product of the two things. And by adjunction, because this is how we define the condensed mapping space, you will get a map from this side to these guys. So this construct a map in this way, but you can also construct a map in the other way. Let me just double check how this is done. Right. So for constructing a map in the other way, well, you just evaluate the profinite sets. Wait for the inverse. Well, just take a profinite set and take F an object in this mapping space from X to Y evaluated at S, which is something on the right hand side. So what is this? So F is equivalent to a map from X cross S to Y as topological spaces. Or maybe first, I should say that as condensed sets. But since X is compactly generated, this map is equivalent to a map of topological spaces. Right, so here is where being compactly generated is used, to just know that mapping from here is the same as mapping from here. But then, let's say it's classical that once you consider this kind of maps and this space is nice, so this gives rise, let's say something classical, to a map from here to this with the compact open topology. Right, whenever you have like this product and this compact open topology is more or less constructed in such a way that you have this adjunction as well in topological spaces. So this construct the map the other way around, and get it to check for you that this actually produces the inverse of this map. So you see, kind of by design, because we took compact Hauser spaces as objects that will generate condensed sets, mapping spaces between reasonable topological spaces is just endowed with the thing that you will expect, at least that is adjunction, which is this compact open topology. Right. Maybe to give, not to prove, because the proof requires some work, but another interesting phenomena that happens for condensed abelian groups, maybe once you look at condensed R modules, is some relationship in classical analysis between, well, Banach spaces And another kind of spaces that are called Schmidt spaces. So we also have an interesting let's say duality in real analysis. Also in p-adic, let me just say real analysis. So let me maybe recall the definition. A Schmidt space our vector space is locally convex real vector space M that contains a convex compact Hausdorff space let me call it M naught, such that M can be written as the union of just a multiplication of this guy like here. So this is a kind of class of two-vector spaces. So for example, if you are maybe follow your course on the I think it's the course on the what's it called this measure theory. Things like radon measures. On compact Hausdorff spaces. Are Schmidt spaces. So for example, you should think about the spaces in particular as those kind of spaces of radon measures on compact Hausdorff spaces. And well, maybe should say signet radon measure or something. You can construct a topology of these guys, kind of a natural topology in these spaces, and it turns out to be one of these ones. So, well, classically, whenever you have two Banach spaces, or let's say just one Banach space, and you take the dual of the Banach space, you endow the dual of the Banach space with a Banach structure, like with a structure of a Banach space as well. And it is well known that if you take the double dual of a Banach space, so this one is going to be isomorphic to the original Banach space if and only if it is finite dimensional.
Maybe you can change the pen.
Yes. Thanks. So let me put this one here. If and only if it is finite dimensional. Well, it turns out that if you put the correct topology, Banach spaces are always reflexive. And well, by correct topology, I would mean like the topology that turns out for condensed Abelian groups. So that's a theorem that I think that goes back to Schmidt. It was reviewed by Clausen and Scholze in these worlds of condensed math. So there is an anti-equivalence of categories between, well, you can take Banach spaces over the reals, and these are called Schmidt spaces over the reals. And the way to do this is, well, if you want, you can take the Banach space that now you can see as a condenser real. So this one is our module. So condense real our module, our vector space. And what you can do is you just map it to the dual of V, but for this condensed structure instead. So for example, and basically these kind of the basic cases, if you take some M compact Hauser space, you can look at the continuous functions of S in values in, continuous functions of M with values in the reals as a condensed real vector space. And by taking duals, in the condensed sense, so like here, well, you will get these precisely these radon measures. Oops. Here. And, well, the functor the other way around is also taking duality. Like, you also take some W and you just map to W2 as well. So, if you want a way to recover the classical statement saying that a Banach space that is reflexive is just a finite dimensional, whenever you put the Banach topology into the dual, you can extend it the following way. So, if you take Banach spaces and you intersect with the Smith spaces, this is just finite dimensional vector spaces. So in other words, if you have the reflexivity with the Banach topologies, because the dual is also, which is naturally a Smith space, is also a Banach space, so it has to be finite dimensional. So by going back again, using this duality, you get this finite dimensional thing. And again, the reason to take this is because like this dual, the natural topology you have as a condensed abelian group is just this compact open topology. So that's good. You don't need to worry anymore about the 10 topologies you have these guys. I think it's 10, I don't know how many of them.
What is that fancy M that you've written? I didn't exactly understand.
This one?
Oh, that's mu.
This is M. That's supposed to be an M of measures.
Oh, measures.
Yes.
So what is the topology that you equate on?
So that's a good question. I will say, well, a clean way to say this is just the compact open topology of this dual. Because for what you saw this. But there are other ways to access to the radon measures, but let me not be sure about that because I actually don't remember. Right. So in the last, I think we started like 5 minutes late, so we can take a little bit time. Okay. In the last almost 10 minutes, let me conclude today with. Well, we'll review some examples very roughly of condensed abelian groups, at least that some internal home behave as with the compact open topology, that you have this kind of funny duality that was already known since the 60s. I mean, this is kind of very old theorem once you put the correct topology in these guys. But condensed math tells you that it also shows up whenever you talk just usual duality of condensed abelian groups, in this case, condensed real vector spaces. And another important feature, an important kind of computations that we always do in topology is, well, just cohomology, right? Care about cohomology of varieties. Let's say cohomology of manifolds first, cohomology of topological spaces. So in these last minutes, we are going to compare cohomology of topological spaces and condensed sets. So again, whenever, I mean, there are actually much stronger statements than just comparing cohomology. You can even compare the right categories of shifts, and they're going to be the same once you properly define them. But let me maybe stick the cohomology. And maybe just make a quick definition that, again, there are many different ways to access cohomology whenever you are in, again, shifts on a site. But maybe the quickest way is this one. So let T be a condensed set and M some discrete abelian group where discrete literally means this is just an abelian group with a discrete topology that I'm going to see as a condensed set. So it's just the natural inclusion of abelian groups into condensed sets. Then the condensed cohomology, and maybe just let me just write condensed groups. of t with values in m. Well, a way to access to this is just by taking extra of the free condensed abelian group values in m. Like this is something that will probably fall for my finite junction. All right. So well, classically, given X a topological space, you have different cohomologies. Again, just following what is written in condensed notes. So you have, for example, singular cohomology, which uses singular cochains. Whenever you have like covers by open subspaces, you have a check cohomology of X with n, kind of limit by taking all possible check covers of these things. And another one is the shift cohomology, where you consider M as a constant shift in the topological space, and then you take the shift cohomology. I mean, there's other way to take this. So for X, something like a CW complex, all agree. I think that these two, if you're careful enough, you can also make it agree. Maybe I think you may need to take a little bit more, something more refined, maybe after passing to upper cover something. Let's say upper covers. Maybe you need, yeah, let me just say that, using upper covers. If you know what this is, well, I invite you to look at these definitions. These ones are very useful. But singular cohomology, for example, if S is profinite, I think that, for example, the H naught in singular chains of S in M is just all the functions from S as a discrete set to M. So there is not much. But the shift cohomology of S in M is just the continuous functions from S to M. So meaning the locally constant functions. So of course, like this one looks like something more natural to have the just random functions in a profinite set, because this one does not make a difference between S and the S with the discrete topology. Well, basically because singular cohomology, you define it by looking at maps from path connected spaces, and this one is totally disconnected. So the shift cohomology is like the best, at least in what definition regards. This one is maybe very useful for doing algebraic topology, but well, at the end you're computing this one anyway. And well, you can compare these two cohomologies, at least for a very large class of topological spaces, at least for those that you actually want to compare the cohomologies, not for random things.
So it's like these condensed sets. So are you doing C of t as, so how are you exactly doing?
C of t, recall, is the free condensed abelian group generated by this condensed set T.
Right, but it's still a sheaf, right?
It's still a sheaf, yes, it's still a sheaf.
How does x of z of t comma m, where m is a top?
So again, like whenever you have, in this case, a rotating abelian category, there is some kind of internal notion of having just x functors. For example, a way to compute this thing is by resolving the right-hand side in terms of injective objects. And then you compute the x by using these injective objects. So whenever you're having these nice rotating abelian categories, like all these x functors and so on, they are always defined. You can always like make it this way, using injective objects, for example.
Okay.
For example, you need to resolve this in terms of injective models.
In this last equation, what is the exponent of C
Sorry, it's supposed to be locally constant, an LC. So there is the proposition is that let X be a locally compact Hausdorff space so space that has open neighborhoods that also compare with compact neighborhoods. Then an M, some discrete abelian group. So then there is a natural isomorphism between the condensed cohomology of X, I've just defined using these X functors, and the shift cohomology of X as a topological space with values in them. So indeed, condensed cohomology also recovers a shift cohomology. We told you that at least in what, taking, let's say, mapping spaces or duals of reasonable topological abelian groups, it behaves as very good. In terms of taking cohomology, it also behaves very good, but, well, maybe let me address something much stronger. You can consider X and define some kind of, well, let me just say the condensed site. Which are just profinite sets which are mapped to X, and the covers being the usual covers that you have here. It's just profinite sets mapping to X. Then, well, you can compare the right categories of this condensed site. Let me set like the right categories. And maybe let me take just the left-bounded derived categories of shifts on this site. And this derived category is actually isomorphic to the derived category of X as a topological space. Here. So not just you can compare cohomology, but actually you can compare the derived categories itself, which basically this statement will imply this statement in here, by just taking just cohomology of like this M as a constant shift here. So this condensed theory is actually more powerful, not just because shift cohomology, but actually you get the whole derived categories inside. Well, if you, I mean, this kind of, what's going on here. Okay, so just maybe remark for tomorrow. So tomorrow the idea is, well, because I address this problem of that the tensor product in condensed abelian groups is not complete. So the idea is tomorrow to address this inconvenience. So actually define, in some sense, completed tensor products that are going to be used in algebraic geometry and at least p-adic geometry. Well, but this one is going to be for that. Okay, I'm going to stop here. Thank you very much.
So, are there any questions? Okay.
You define the cohomology on condensed as an X?
Yes?
Maybe what is that cohomology on the theory to something more concrete? Why is reasonable to take that as a definition?
Right, so a cohomology in degree 0 should use the eraser. So again, the way I define this was by taking this, at least, well, that was the definition. Hi was the xi in condensed abelian groups of a set of T with M. But if you take I equal to 0, the H naught of condensed upon t with values in M is the same as from set of t to M. But recall that this object was constructed such that it was a left adjoint of the forgetful functor. So by adjunction, this is the same as maps from t to M. Okay?
So what you write there is like the motivation, like
No, this one just was kind of a justification of why we're taking shift cohomology instead of other cohomologies, instead of other definitions.
the degree zero cohomology are like functions.
Right, like degree zero cohomology is functions, the higher ones doesn't matter. And here one, the degree zero are the continuous functions. This is also the same as the continuous functions. Because M is discrete. So locally constant maps are the same as being continuous for a profinite set. Which is exactly the same as this, yes. Exactly the same as this one, exactly.
Can you say something more about you were explaining about the derived categories? And
Yes.
Why is that?
Why is that important?
Yeah.
I can tell you different reasons why the right categories are important. So the first one is that within this realm, you cannot just look at, for example, you can define a cohomology just by working inside the right categories, but you can get something much more interesting, which are local systems, these right categories. And for example, there are very deep theorems in Hodge theory that relates these local systems with differential equations, something, for example, like Riemann-Hilbert. So yeah, the right categories show up everywhere in arithmetic geometry, I would say. Another reason that is different from that is that by promoting this construction to something more fancy, which are stacks, not just condensed sets, but condensed anima, you also will find representations, smooth representations of profinite groups, for example, something that we care in the Langlands problem number theory. And they also can be built up using this formalism.
You said that it has a classical argument to from a condensed set map 0 map x to y. You can construct a map that is continuous, right?
Mhm.
Classical argument. I wonder if this classical argument relies on an approximation, or how can you induce a continuous function from a
I mean, the thing is that there is only one map you can define, which is an evaluation map, or a map from into S to the mapping space. And this map is kind of just something that comes from sets, and then what you have to prove is that this map is continuous. And that is something for which you need this kind of conditions that is put here. Once you just want to prove that this one is continuous, and for that, well, you just go from the definition of what the topology in this mapping space is, and you maybe need to use some of the actions I just stated, and this is something you get. But the map is just the map that you get from sets for topological spaces.
So the evaluation map is already continuous by some argument. And
The evaluation map,
the topology, so it's continuous.
right, in the topology side is going to be the continuous. This is something that for which you endow this object with a compact open topologies, kind of for making this point, at least one of the motivations is to make this map continuous, for example.
All right.
But this map is just the evaluation of sets, which is already something that existed beforehand.
And the other map is just the injection from the continuous map to is the natural map.
The other side, you mean?
Yes.
Well, it's more like, I think for that one, I mean, one I like it because it's just the junction of a product. The other one, I think you actually need to take points, and then for S points for a profinite set, you actually construct like an object in the other arrow. So it's more like trying to make the inverse of this map. It's, I mean, both of them are so explicit enough to be constructed. But
Perfect.
Actually, before we thank Juan, we will give you some information about
Yes.
the asado. So, but first, let's thank Juan again.
maybe not as exciting as Ian's letter of cross again, but it's still important enough for today.
No, no, no. Okay.
Okay, it's in there.
So, okay, again, the street is over here. I mean, you can find it, of course, in the website. And just something I might forgot to tell you is that you have to pay an entrance. It's like $0.50, okay, or €1, or whatever. Okay. And here we have a little bit of the map of the bay where we're going to do the asado. So, Dante, can you please go a little bit down? We have technical problem, but you can more or less see here. So